So one of these questions was something like use implicit differentiation. Compute, yeah. Blurry, thank you. Let's get that unblurified. There we go, much better. Use implicit differentiation. Compute the tangent. And we'll just do the tangent line of the equation. Let's say we have 4x squared plus 9y squared equal to 36. And the issue with this question, at least from my vantage point, is they didn't give you a point of tangency. This equation is the equation of an ellipse. It looks vaguely like this, where the y-intercepts are plus or minus 2, the x-intercepts are plus or minus 3. So there's our ellipse. But they didn't actually tell us the point of tangency. So what we're going to do is we're going to make one up. Say, cool, let's call this the point x naught comma y naught. Or a comma b, or whatever you want to name it that isn't just x and y. And we do need to not use x and y specifically here. So usual stuff. We're going to find the slope. So to find the slope, we're going to find the derivative. So we're going to differentiate both sides of this equation. We're going to get 8x plus 18y times y prime, or dy dx, equal to 0. Just taking the derivative of both sides implicitly, assuming y is a function of x. Then we're going to solve for y prime, or dy dx. So we're going to get the dy dx is equal to negative 8x divided by 18y. I'd probably simplify that a little bit and say it's equal to negative 4x over 9y. That's our slope anywhere, but we're trying to find the slope at this particular point. So somewhat annoyingly, the slope at the point x naught comma y naught, we're just going to plug in x naught and y naught and say it's negative 4x naught over 9y naught. You might throw in the caveat that y shouldn't be 0. So we don't get division by 0. If y was equal to 0, we'd be over here or over here, where we have a vertical tangent line with an undefined slope. So then to write our equation, and again, this is not going to be very nice, that's our slope, that's our point. Point and slope form, y minus y naught equals your slope times x minus x naught. If you want to isolate y, which we sometimes do, we'd write it as y equal to y naught plus negative 4x naught over 9y naught times x minus x naught. Again, assuming that y naught is not equal to 0. Not a great question. But that's how you would answer it if you weren't given a point. You would make up a point that was general. All right. So the plan for today is to talk a little bit more about derivatives of inverse trig functions, and then to talk about related rates. So let's talk a little bit more. Specifically, I want to address the thing about inverse secant and inverse cosecant because it is a little bit strange. I don't want to spend a whole lot of time on it, but I do want to spend a little bit of time, and then we'll move on. So let's talk about the graph of secant of x for a second, which is never my favorite graph, but here's how I would address it. Whenever I'm trying to graph secant or cosecant, I'm really just thinking about sine or cosine. I should say cosine or sine specifically. For secant, I'm thinking about cosine. For cosecant, I'm thinking about sine. So I want to graph y equal to secant of x. What I'm secretly, not so secretly going to do is graph cosine. So cosine is a period of 2 pi. I'm going to go from negative 2 pi to 2 pi. And then remember that cosine starts at 1, goes down to negative 1. So it's going to look something like this. Like that. Same deal over here. Looks vaguely like this. Maybe a little bit better than that usually, but okay. There's our cosine graph, or the outline of our cosine graph. And I'm remind you that secant is the reciprocal of cosine. So if cosine of x is equal to 1, secant of x is also going to equal 1, because 1 divided by 1 is 1. And then, as the cosine values get smaller, the secant values get larger, because 1 divided by a small number gets really, really big. So as cosine of x approaches 0, 1 over cosine of x gets really, really large. Like infinitely large. Like we're going to have a vertical asymptote at the places where cosine is equal to 0. So pi over 2 and 3 pi over 2 and any odd multiple of pi over 2, just like with tangent, we're going to have vertical asymptotes. And what I really think about here is that the secant kind of looks like we took the cosine graph and flipped it away from the horizontal x-axis. Instead of going downward like that, we're going to go up like that and up like that. As cosine gets closer to 0, secant gets further away from 0. Same thing down here. If cosine is equal to -1, 1 divided by -1 is still -1. And then as cosine gets closer to 0, secant gets further away from 0. And that's what one period of the secant graph looks like. Kind of weird, but not that weird. Just as a real quick note, those are not parabolas. They kind of look parabola-ish, but parabolas don't have vertical asymptotes, and these definitely do have vertical asymptotes, so they're not parabolas. They just have a kind of a similar shape. So now here's the question that begs asking if we're trying to graph the inverse secant function. What domain do we pick? And the problem here is there is not agreement about which domain gets picked. One plausible choice is to pick the stuff starting at 0 and ending at pi. So if we did just this piece and just this piece, so we take our domain to be everything from 0 to, technically we have to stop at pi over 2 and not include pi over 2. And then back from pi over 2 to pi. If we take that as our domain and then invert it, here's what we get. Now I'm looking at that piece and that piece. I have a horizontal asymptote at pi over 2, which is going to turn into, sorry, I have a what? I have a vertical asymptote at pi over 2, which is going to turn into a horizontal asymptote at pi over 2. And then the point 0, 1 becomes the point 1, comma 0. And we go this way. And the point pi -1 becomes the point -1 pi. And we go this way. It doesn't look as symmetric as I'd like it to because I didn't extend this one far enough. That's one way of graphing f of x equal to the arc secant of x or the inverse secant of x. And as I said last time, this graph, any tangent line would have a positive slope. So every derivative has to be positive here. So if we write it this way, then our derivative is going to equal 1 over the absolute value of x times the square root of x squared minus 1. Which we did at the very end of class last time. We'll talk more about that in just a second. The other plausible choice that you can make here, which in my opinion is the less nice choice, is we could have picked our domain to be everything from 0 to pi over 2. So still getting this bunch right here. But then instead of getting this piece to the left of pi, we're going to get this piece to the right of pi. So we're going to go from pi to 3 pi over 2. It's kind of weird. So now the right half of our inverse graph still looks the same. I didn't really leave myself in the, well, I should draw my horizontal asymptote before I get too carried away here. So we have a horizontal asymptote at pi over 2. And then we're also going to have a horizontal asymptote at 3 pi over 2. And we're still going to get the point -1 comma pi, but instead of coming down like that, we're going to go up like that. Kind of weird. And the difference between this graph and this graph, I mean, there's obviously a lot of differences, right? You can see the difference. But as far as the derivative is concerned, on the left side here, the derivative is negative. That function is decreasing. On the right side, the derivative is positive. So what we would say here is that our derivative is 1 over x times the square root of x squared minus 1. If x is negative, this quantity will be a negative value. If x is positive, this quantity will be a positive value. So it's kind of weird. I don't love that there's ambiguity here. Hopefully your instructor has said something about it, maybe. But if they haven't, I would say probably shouldn't worry about it too much. I would probably default to putting the absolute value if you didn't know any other better way to do it. That's usually where I default to. But yeah, that's all I really have to say about that. So let's make a quick list of our inverse trig derivatives. And I think that's pretty much all the functions you ever have to take the derivative of. Unless your instructors talk about the hyperbolic trig functions, which really aren't trig functions. They just kind of have some similar properties to trig functions. So if your teachers say something about hyperbolic trig functions, let me know. Otherwise, we won't bother. I didn't learn about them when I took Calc 1. I was like, what are these things later on? They're really not that big a deal, but they're kind of neat. So here is our list of derivatives of inverse trig functions. And then we'll talk about some related rates. So we have the derivative of the inverse sine of x is equal to 1 over the square root of 1 minus x squared. The derivative of the inverse tangent of x is 1 over 1 plus x squared. And the derivative of the inverse secant of x is equal to 1 over the absolute value of x times the square root of x squared minus 1. Or, depending on how it's defined, 1 over just regular x times the square root of x squared minus 1. And there's a reason I've only written these three first. The other three are pretty much just you get for free. The other three are all negative of what these ones are. So the derivative inverse cosine is negative 1 over the square root of 1 minus x squared. The derivative inverse cotangent is negative 1 over 1 plus x squared. The derivative inverse cosecant is negative 1 over the absolute value of x to the square root of x squared minus 1. So the derivative of the inverse cosine of x is negative 1 over the square root of 1 minus x squared. The derivative of the inverse cotangent of x is negative 1 over 1 plus x squared. And the derivative of the inverse cosecant of x is negative 1 over the absolute value of the square root of x squared minus 1. Or if you prefer, negative 1 over just x to the square root of x squared minus 1. Which is kind of nice because if you remember the regular trig functions, sine, tangent, and secant have positive derivatives, and the other three co-functions, cosine, cotangent, and cosecant, have negative derivatives. It's kind of convenient that that pattern still holds here, that the regular inverse trig functions have positive derivatives, and the co-inverse trig functions have negative derivatives. So it's nice to see that pattern is kind of sticking around for us. So knowing this, we can then answer questions that are more of a chain rule kind of version, like, for example, what's the derivative of the arc tangent of e to the 3x? Well, we know the derivative of the arctangent of x is 1 over 1 plus x squared. So the derivative of the arctangent of some stuff is going to be 1 over 1 plus our stuff squared times the derivative of our stuff, which you can probably skip writing it that way and just write it as 1 over 1 plus e to the 6x times 3e to the 3x. Not too terrible. Why don't you all try finding the derivative of the arc cosine of x to the 4th power? X to the 4th. So just recalling the derivative inverse cosine of x, derivative inverse cosine of x is negative 1 over the square root of 1 minus x squared. So the derivative inverse cosine of x to the 4th, or arc cosine of x to the 4th, is going to be negative 1 over the square root of 1 minus our stuff squared times the derivative of our stuff. You could leave it like this. You could also simplify it as negative 4x cubed over the square root of 1 minus x to the 8th. So when you take 21b and you see something like find the integral of 4x cubed over the square root of 1 minus x to the 8th, you're going to do a u sub and you're going to let u equal x to the 4th. And the reason you're going to let u equal x to the 4th is because you're going to see, oh, the derivative of x to the 4th, which is 4x cubed, is showing up in my integral. We'll definitely talk about that again next quarter, but just kind of as a preview as to kind of how you approach some things later on, that's something we look for. We'll also point out these inverse trig derivatives help us know how to do things in the future. The reason that sine corresponds with 1 over square root of 1 minus x squared is because if you let x equal sine, 1 minus sine squared is equal to cosine squared. Here, if you let x equal tangent, 1 plus tangent squared is equal to secant squared. Here, if you let x equal secant, secant squared minus 1 is equal to tangent squared. Those trig identities are showing up for a good reason, and they're going to show back up next quarter. So I really, really, really recommend not spending like a ton of time memorizing these, but definitely making sure that you remember these, because these quantities, 1 minus x squared, 1 plus x squared, and x squared minus 1, do show up later, and it's important that you kind of make the connection between these quantities and those trig functions. Specifically the ones on the left, not the ones on the right. Not that you couldn't use those ones, but the left ones are better because they have positive derivatives. That's why they're better. All right, let's go ahead and I guess we could throw one more in here. I didn't do an arc secant, sure. So let's find the derivative of, sorry, throwing my pen everywhere. Derivative of the arc secant of x divided by e to the x. I'd really rather not use the quotient rule. So let's rewrite it as the derivative of the arc secant of x times e to the negative x. If it's easy enough to bring your denominator up to the top and it's like not that much worse, I would recommend doing that to avoid using the quotient. So now, for the derivative of arc secant of some stuff, it's going to be 1 over the absolute value of your stuff times the square root of your stuff squared minus 1 times the derivative of that stuff, where we're going to use the product rule. So the derivative of our x e to the negative x is going to be the derivative of x times e to the negative x left alone, plus we switch it up, leave x alone, and the derivative of e to the negative x is e to the negative x times -1. And I don't think I would take the time to simplify that. It's not like terrible, but who cares? You all have a test next week, I think. Some of you on the 26th, some of you on the 28th. Sounds right. Okay, Wednesday and Friday. So next Tuesday, I guess we'll do some review for your exam. But the point I was going to make, there's reason I was thinking about that. The point I'm going to make is on this exam, it will be probable that you'll have some questions where it'll be like, find the derivative, don't simplify your answer. Don't simplify your answer. It's going to take time, and it's also it's just an opportunity to lose points, right? If they say don't simplify, really, really, really do not simplify. All right, but let's move along because inverse rate functions are not that exciting. Let's talk about related rates. The name is the name for a reason, right? We're going to talk about some rates of change that are related to each other. So typically you're going to be told how one thing is changing and then be asked how another related thing is changing. A very typical first example is talking about a circle that's growing in size. So let's say we have the following. Suppose that the radius of a circle is increasing at a constant rate. You don't really need the word constant there, but it's not terrible. Of 3 feet per second. How fast is the area of the circle increasing? When the radius is 10 feet or 20 feet. So when I approach a related rates problem, I usually kind of like to follow like 4 or 5 step process. Sometimes I like to draw a picture. I don't feel like it's super necessary here, but I'm still going to do it anyway. For a circle that's getting bigger, you can draw a circle. Okay, cool. My circle, there it is. It's getting bigger. It's growing outward. So like my radius here, whatever it is, my radius is increasing. It's going that way. Labeling things that are changing as appropriate. We'll talk more about that for more complicated problems. And then the first step really is to kind of figure out what's changing and how we're going to label that. So the thing that they told us how it's changing is the radius is changing. I don't know why. How is the radius changing? Well, it's increasing at 3 feet per second. So we're going to say that the rate of change of the radius, that is dr dt, is equal to 3 feet per second if you like, but we don't really need the units. Okay. Typically, there's going to be one thing that you're told how it's changing, and another thing that you're asked to find how it's changing. The other thing is going to be the area of the circle. So the area is also changing. So are other things, right? The circumference is also changing. The diameter is also changing. But we kind of want to focus on the things we're being told and the things we're being asked about. So the area is also changing. We don't know how, so I like to write dA dt, and since I don't know what it is, it's going to be question marks. I do know that the unit should be square feet per unit of time. Right? If it's an area, it's whatever your unit is squared divided by your unit of time. It's most of the time it is with respect to time. Like usually we're asking about how something is changing as time goes on, but there are other possibilities. Like you could talk about like pressure and volume changing as you like increase your altitude. That's another way you can kind of write a related rates problem where you don't have time involved, but most of the time it's going to be time. All right, so now after you figured out what's changing, you want an equation relating the non-time variables. So we need an equation that relates area and radius. Usually it's some geometrical formula. usually like the area of the circle, or the area of a triangle, or the volume of a sphere, or the volume of a cone, or a box, or a rectangle, or the Pythagorean theorem. Like those are the typical kind of geometric things that show up in these problems. Some sort of area or relation between distances formula. So in this case, our equation relating area and radius is going to be the equation for the area of a circle. Area is equal to pi r squared. And now we're going to differentiate both sides. And there's a couple ways you could approach this. I'm going to show you the most typical way and then talk about a few other things here. So we're going to differentiate both sides. Differentiate both sides. With respect to time. Time is the thing that's moving forward. So we're really asking, how is area changing as time increases? How is the radius changing as time increases? So with respect to, that's what the WRT means there, with respect to time. This is where people get a little bit tripped up. When we take the derivative of both sides, the derivative area isn't 1. Right? The area isn't increasing at a rate of 1 square foot per second. It's variable. The derivative area is the derivative of area. It's kind of like we're doing implicit differentiation. On the other side, pi r squared, the pi hangs out. The derivative of some stuff squared is 2 times our stuff to the first power times the derivative of our stuff. I want to point out something kind of cool. This is where the chain rule, the alternate version of the chain rule that we talked about a little bit, actually comes into play. You could totally think of this as dA dt, I know it's still the same thing, equals dA dr, the derivative of a with respect to the radius, derivative of pi r squared is 2 pi r, if you're not thinking about time, times dr dt. And then if you wanted to imagine the dRs on that side canceling out, you'd have dA dt equals dA dt. So if you didn't want to think of it this way, you could just be like, hey, I know it's going to be that dA dt should equal dA d, whatever the middle thing is, and times whatever the middle thing is, dt. You can always kind of make that middle choice to be whatever you want it to be, that we need it to be. I don't particularly love doing it this way, but it does kind of emphasize the nature of that chain rule formula we learned earlier. Or another way to think about this is you could have said, I know both of these are really functions of time. I could think of this as area as a function of time equal to pi times radius as a function of time squared. And then when you differentiate both sides, you get a prime of t, or dA dt, equal to pi times the derivative of r of t squared is 2 times r of t to the first times r prime of t. It's the same formula, just written using different notation. But this first way I wrote it is the pretty standard, typical way of doing it. Cool. After you get there, then we want to plug in the things we know, solve for the things we want. You should always be able to plug in for everything except for the one thing you're trying to find. And if some things feel like they're missing, we often have to go back and kind of find them. So here we're going to plug in, and I should stress, you can't plug in until after we have taken the derivative of both sides. Now, if you plug in first, then everything's just constant and your derivative is going to be 0. But we plug in now, we're going to get dA dt on the left equal to 2 pi times the radius, which is 10 feet, times dr dt, which is 3 feet per second. I didn't write the units, they didn't want to, but then 3 times 10 times 2 is 60, so dA dt is equal to 60 pi feet squared per second. And we know it's feet squared per second because it's 10 feet times 3 feet per second. Feet times feet is feet squared. And then if it was the other situation with 20 feet, same idea, dA dt would equal 2 pi times 20 times 3, which is going to double this value. And it's going to be 120 pi square feet per second. Which makes sense, right? If the circle is bigger. No? Okay, fine. God, sorry. If the circle is bigger, then and it grows, by some same amount of radius, then you're going to get that much more area because you're further out, right? A smaller circle, if you add like an inch of radius, you don't get that much more. A bigger circle, if you add an inch of radius, you get a lot more area. And I don't know what I need to do to make this work again, except for wave my arms around. Sorry, this technology is not being very agreeable today. Maybe. Questions while I try to make this work. There we go. Nope. Nope. It'd be funny if it wasn't so annoying. Yeah.
I have a question about like when you get the 10 plugged into the
Get the what?
10.
Oh, the 10 was given in the problem. Yeah, if I would show you if I could. So I guess I'll just try plugging this in this other way. I think my battery will last long enough now that I don't have to worry about it. The problem is plugging in with this other thing. I have to move the battery. Yeah, I'm worried about my laptop if this HDMI port is not working so well. Maybe. Okay, there we go. Back in business. So yeah, that actually is an important question though, in that these problems, the point of something happening kind of has to be given. So in the problem we were given, right, how fast is the area increasing when the radius is 10 feet or 20 feet? Let's see here. There we go. All right, cool. Yeah.
When we differentiate both sides, so the pi is a constant, so we leave it without.
Right, because it's not just a constant, it's a constant multiple of a variable.
Oh. And why is it 2r times r prime and not just 2r?
So that's kind of why we're like this here. If you look at it this way, the derivative of this function r of t squared, we have to use the chain rule. The derivative of some stuff squared is going to be 2 times our stuff to the first power times the derivative of the inside stuff. You should always be thinking of these implicit problems like these related rates problems like it's implicit differentiation. It's always implied that the things we're talking about changing are typically functions of time. So whenever you're differentiating with respect to time. So if I had r cubed, the derivative would have been 3r squared times dr dt. Let's look at another example. Try not to like jinx myself over here by touching a chord. All right, so another example. A spherical balloon, a sphere is being inflated by increasing the volume at a rate of 10 cubic inches per second. Right, we're filling it with what, helium, right? Not hydrogen, helium. Filling it with helium, let me save. How fast is the radius of the sphere changing when the radius is 6 inches? Okay. Again, another example where it's probably not super necessary to draw a picture, but we could anyway. So here is our spherical balloon. And the radius is increasing. Getting larger and larger and larger. So we're told a couple things here. We're told how the volume is changing. So we know that dV dt, the rate of change of the volume, is going to be 10 cubic inches per second. And we're being asked how the radius is changing. I do think it's a good idea as you do these problems to think about if your answer should be positive or negative. In this case, since the balloon is getting bigger, the radius is increasing. Sometimes with other problems, it's a little less obvious if things are increasing or decreasing. So it's good to actually think about it. So now we need the equation relating the volume of the sphere and the radius of the sphere. And that's an equation that's equal to volume is going to be 4/3 pi r cubed. Probably something you should memorize. Okay, now we're going to differentiate both sides. The derivative of volume isn't just one, it's the derivative of volume. So here's what I would actually say about this. Let me back that up. We just talked about how we know that dv dt is equal to 10. We're trying to find dr dt. Those things should show up in our derivative, right? The thing we know and the thing we want to know should both be pieces that appear after we differentiate both sides so that we are able to figure out what's going on. So when I differentiate volume, I get the derivative of volume. When I differentiate 4/3 pi r cubed, I get 4/3 times pi, that constant hangs out. And the derivative of r cubed is going to be 3 times our r squared, but then we have to multiply by the derivative of r with respect to t. And yeah, we can cancel those 3's. Interesting fact, this is kind of a not super important fact right now, but it is interesting. The derivative of 4/3 pi r cubed is 4 pi r squared, which is the surface area of a sphere. A similar thing that's true about circles. What's the area of a circle? What's the circumference of a circle? 2 pi r. The derivative of pi r squared. It's kind of neat. It only works for those shapes, right? It doesn't work for a cube, right? The volume of a cube is x cubed. The surface area of a cube is not 3x squared, it's 6x squared. But spheres and circles are kind of special in that you're kind of getting the most amount of volume for how much surface area you're using, or the most amount of area for how much circumference you're using. And so there's this kind of neat relationship that the derivative of the larger dimensional thing ends up being equal to the lesser dimensional thing. Kind of cool. Useful? Maybe, I don't know. Anyway, we've got our equation. Now we're going to substitute in things we know and solve for the things we want to know. So I know that dv dt is equal to 10. So I'm going to say that 10 is equal to, I'm going to cancel the 3's here. 10 is equal to 4 times pi times the radius is 6 inches. So it's going to be 6 squared times dr dt. I will point out, I'm not going to write the units, but I will point out that on the left-hand side, this is going to be cubic inches per second. And over here, that's inches squared. And inches cubed divided by inches squared is going to give me inches per second. So that's going to make sense. And my units for how the radius is changing is going to be in inches per second. It's always kind of nice to think about the units here because it can help you figure out if you're on the right track or not. So then the 36 times 4 is what? 72 times 2, which is 144. So we have that 10 is equal to 144 pi times dr dt. So we end up getting that dr dt is equal to 10 over 144 pi inches per second. Yes, you could reduce that to 5 over 72 pi, but who cares? So most of these problems, the process is always these kind of 4 or 5 steps. Draw a picture, you figure out what's changing, write an equation relating those things. You plug in you differentiate both sides before you plug in. Then you plug in the things you know, solve for what you want to know. Yeah.
Why isn't it cubic inches anymore?
So let's actually write. So if we look over here, right, our equation was 10 cubic inches per second equal to 4 times pi times 6 squared is 36 inches squared times dr dt. Right? When I square those 6 inches, I get 36 square inches. And then when I divide inches cubed by inches squared, I get inches to the first. I usually don't actually do the units, but I think about like, okay, well, at the end of the day, I'm asking how this radius is increasing. Well, the radius is measured not in inches cubed or inches squared, but just in inches, right? Because it's a measure of length, not area, not volume. So we need to think about what kind of thing we have, if it's 1, 2, or 3 dimensional typically, and then use the appropriate units that we need. All right, let's look at something that's a little bit more interesting. Sure, you're fine. How much time have we got? Oh, we still got plenty of time. So let's look at a problem that's a little bit more involved. The radius of a cylinder is increasing at a rate of 3 inches per minute. And the height is decreasing at 4 inches per minute. How fast is the volume of the cylinder changing when the radius is 8 inches and the height is 5 inches? So we have a cylinder. And the radius is getting bigger, so we're kind of moving, we're going outwards like that. But the height is decreasing, so we're also shrinking down like that. So here's our height. Here's our radius. And we know the following. We know that the rate of change of the radius, dr dt, is 3 inches per minute. And the rate of change of the height, dh dt, is negative 4 inches per minute. Right? If something's decreasing, its rate of change is negative. And then we're asked to find, how is the volume changing? So we need an equation relating these variables: volume, radius, and height. Or in other words, we need the volume of the cylinder equation. Cylinders are pretty straightforward. It's always the base area multiplied by the height of the cylinder. So in this case, our volume equation is going to be that volume is equal to the base area is a circle, pi r squared, multiplied by the height. And since we're told all the information about both variables, we can kind of just do the things from here, meaning we can take this equation and differentiate both sides. So taking the derivative of both sides, we're going to get dv dt on the left. On the right-hand side, the pi hangs out, but then the derivative of the product, r squared times h, is going to require the use of the product rule. So the derivative of r squared is going to be 2r times dr dt, right? We still have, right? It's some stuff squared. The derivative is 2 times our stuff times the derivative of our stuff times h plus, then we switch it. We leave r squared alone and we multiply by the derivative of h, which is just dh dt. So just so everyone's on the same page here, we'll just go so right, this is the derivative of r squared times h, and this is the derivative of h times r squared. Product. Now we're going to plug in what we know, solve for what we do, right? It's the same 5 steps. They just can be more or less complicated depending on what's going on. So dv dt is going to equal pi times, let's see, the radius is 8 inches, the height is 5 inches. So we're going to have 2 times 8 inches times dr dt, which is going to be 3 inches per minute, times h, which is -4. Sorry, times h, which is 5 inches, apologies, plus r squared, which is going to be 3 squared. Sorry, not 3. R is 8, good God. 8 squared times dh dt, which is -4. I want to point out here that even though I didn't write the units, these units are inches cubed per second because I have Here I have R, that's 8 inches. That's 3 inches per minute. And that's 5 inches. Oh yeah, inches times inches per minute times inches is going to be inches cubed per minute. Same deal over here. Inches squared times inches per minute is going to give you inches cubed per minute. I will say again, you don't really need to think about that. If you look over here like, okay, I'm asking how volume is changing, it's not going to be inches or square inches. It's going to be cubic inches per whatever the right unit of time is. And I should say it's your unit cubed, whatever the unit is, divided by your unit of time. Simplifying this, we get pi times, let's see, 2 times 8 times 3 times 5 is going to be 240. And 8 squared times -4 is going to be 2 to the 6 times 2 squared 2 to the 8, -512. No, -256. So we end up getting -16 pi cubic inches per minute. Double check my work here. Yeah, cool. Meaning that the volume is decreasing. So a couple ways of writing this answer is you could say the volume is changing at a rate of -16 pi cubic inches per minute. Or if you want to use more words, you could say the volume is decreasing at a rate of 16 pi cubic inches per minute. Either way is fine.
Why do you differentiate?
So I didn't differentiate the pi because I'm using the constant multiple rule. For example, if I was taking the derivative of, sure, 6 plus x squared, the derivative of 6 would be 0, right? 6 on its own is a constant, it's going to be 0. 0 plus 2x. On the other hand, if I take the derivative of, say, 6 times x squared, what do I get? I get 6 times 2x, which is 12x. Right, that 6 that's a constant multiple hangs out. What's really happening here is we're using a shortcut of the product rule. If you really wanted to, you could say, hey, product rule, the derivative of 6 times x squared is going to be the derivative of 6 times x squared plus 6 times the derivative of x squared. The derivative of 6 is 0. So we get 0 times x squared plus 6 times 2x, which is going to be 0 plus 12x, which is 12x. So when you have a constant multiple, I like to say it hangs out. So in the same sort of way, for that previous one, when I was taking the derivative of, say, pi times r squared times h, what I'm really thinking of doing is saying, well, I could use the product rule when I take the derivative. I could say it's going to be the derivative of pi times r squared times h plus pi times the derivative of r squared times h. But what's the derivative of pi? 0. So this whole term is 0. So I really just get, oh, sorry, I forgot the derivative there. I really just get my constant pi hanging out multiplied by the derivative of the thing that's actually the function. So yes, it's the product rule, we just never really use it. It's actually called the constant multiple rule. So very, very broadly, when you have a constant multiplied by a function, that constant just sticks around or hangs out.
And then you do the product rule.
Exactly this. Then we're going to use the product rule. So that's going to give me pi times the derivative of r squared, which is 2r times dr dt times h plus h, sorry, plus r squared times the derivative of h. Yeah, exactly. All right. Yeah, let's look at some more examples. So this example is going to start off feeling maybe somewhat similar, but it's going to go very differently. So water is being poured into a conical tank with a radius of 3 feet and a height of 12 feet at a rate of 5 cubic feet per minute. How fast is the water level rising at the moment the water is 8 feet deep. So it's a conical tank, right? It's cone shaped. Typically, when we talk about a cone shaped tank, we imagine it with the point down, like an ice cream cone, right? Like it wouldn't really make a whole lot of sense to be upside down. Not that you couldn't have a tank like that, it would just be weird. Let me read it again. I see some people struggling with it written. Water is being poured into a conical tank with a radius of 3 feet and a height of 12 feet at a rate of 5 cubic feet per minute. How fast is the water level rising at the moment the water is 8 feet deep? Apologies for my less than stellar penmanship. No one to blame but myself. All right, so let's draw our tank. A cone-shaped tank. And the tank has a radius, meaning the radius of the circle at the top is 3 feet. I shouldn't even write R there, really. And the height is 12 feet. I'll say this again. When we label things here, it's important to label things that aren't changing with just their numerical values and things that are changing with variable names. So what we really care about here is the water level that's rising. Right? We're pouring water into this thing, and the water level is rising. So there's the water that's in the tank. And we care about how fast the water level is rising, meaning we care about how fast this height is changing. We might also care about the radius of the circle that's the surface of the water. So what do we know? Good question. What do we know? Well, again, we're always starting off with what's changing. We are told how something's changing. We're told that water is being poured in the tank at a rate of 5 cubic feet per minute. So we know how the what is changing. Well, if we're talking about cubic feet per minute, we're talking about how the volume is changing, right? Dimensions here really help us figure out what we're being told. So we know that the rate of change of the volume of the water is going to be positive 5 cubic feet per minute, right? We are increasing the amount of water in the tank. And then we're being asked to find how the height is changing, the height of the water or the water level, which is the height of the water. So we want to know what dH dt is going to be. Notably, neither of these things are R, right? We don't really care about what the radius is doing. But the radius is still going to show up, unfortunately, because when we find an equation relating the volume of a cone to the height of a cone, well, the equation for the volume of a cone is 1/3 pi r squared times h. And the problem here is that although we could differentiate this one like we did the previous problem using the product rule, we don't know what the radius is or how fast it's changing. And so this type of problem, when you have a cone, typically involves an extra step. We have to figure out how to relate the radius to the height. Fortunately, it's not that terrible. If you look at the big cone, what's the radius of the big cone? What's the height of the big cone? So the radius is 1/4 the height. End of story. The radius is 1/4 the height. Or 3/12 the height. Really what's happening here is we're using like similar triangles. Like if you want to like actually like drop a perpendicular here like this, you could say I have some similar triangles where the big triangle has a base of 3 and a height of 12. And the smaller triangle has a base of R and a height of H. And then you can say something like R divided by H equals 3 divided by 12, and then solve for R and get R equal to 1/4 times H. Yes, you could do all that work or you could not. You can say, hey, the radius is 1/4 the height, and write out that mathematical statement. And that always will work for cones, right? For a cone, the radius of the cone and the height of the cone are always in the same proportion to each other, no matter how big or small your piece of water in the cone is. So then what we're going to do is we're going to replace the radius with 1/4 the height. Why not the other way around? Because we're being asked how the height is changing, not how the radius is changing. So we want our equation to have volume and height, not volume and radius. So we're going to have the volume is equal to 1/3 pi times 1/4 h quantity squared times h. And now we're going to multiply it out to make it a little bit easier to differentiate. 1/4 squared is 1/16, and 16 times 3 is 48. So we're going to have volume equal to pi over 48 times h squared times h is h cubed. Much nicer to differentiate. So now we're going to differentiate both sides. We're going to get dv dt equal to our constant pi over 48 is just going to hang out in front. And the derivative of some stuff cubed is going to be 3 times our stuff squared times the derivative of our stuff. Now we plug in for what we know, solve for what we don't. So we're going to plug in 5 for dv dt. And 8 for h. And then solve for dHdt. It's a little bit gnarly looking. Yeah. We can simplify this right-hand side a little bit. 3 times 8 times 8. I wish I had a little bit more room here. So 5 equals pi over 48 times 3 times 8 times 8 times dH dt. 3 times 8 is 24. And then 8 divided by 2 is 4. So we really have 5 equal to 4 pi times dH dt, which means our dH dt is going to equal 5 divided by 4 pi. And then we put in the units. We're talking about how a height is changing. So that's a length, not an area, not a volume. So it should be our unit of measurement divided by our unit of time. So in this case, it's going to be 5 over 4 pi feet per minute. And just to kind of say again how I did this cancellation here, I saw that 3 times 8 was 24. 24 and 48 cancel out, leave 2 in the denominator, and then the other 8 divided by 2 gives me a 4 left over there. I'm trying to make the math less terrible, not more terrible. All right. Sure, let's look at one more and then we will call it a day. Yeah, I like this. Sure, I like this one, right? Yeah. I feel like maybe it was no, I think it was actually, I think I'm thinking of something else. All right, that's fine. So one more of these. Yeah, let's look at one more of these. So here's the problem. It's a little bit more complicated. At 8 a.m., Ham is 31 miles west of Rolf. Ham walks east at 4 miles per hour, and Rolf walks south. So walks south at a rate of 5 miles per hour, which is pretty fast to walk. Find the rate at which the distance between them is changing at noon. We definitely need to draw a picture here. So let's see. The 8 a.m. Pam is 31 miles west of Rolf. So they're starting out. Pam is over here. Rolf is over here. They're 31 miles apart. And Pam is west of Rolf. Yes. Okay. Let's see. Now, Rolf is going to walk south at a rate of 5 miles per hour. And Pam is going to walk east at 3 miles per hour. And then we're asking how fast is the distance between them. So this distance here, how fast is that distance going to be changing? Okay. So it's kind of funky how we set this one up. So let's say we're looking at a snapshot in time where Pam has moved over and Rolf has moved down. So we actually need to label some things so that we have like something. So let's move over to where we've moved forward in time, and now instead of Pam being over here and Rolf being over here, now Rolf is somewhere down here, and Pam has moved to be like, say, like right here. These distances, say X and Y, are changing. We have to be able to label something that's changing. So as Rolf walks down south, is Y getting bigger or smaller? Bigger. So we can say that the rate of change of Y is how fast Rolf is walking, which is going to be 5 miles per hour. As Pam walks to the east, is X getting bigger or smaller? Smaller. So we're going to say that dx dt is how fast Pam is walking, but it's negative. It's going to be -3 or -4, sorry, miles per hour. Now we should also label the side that we want to know about. I would probably call it Z. So we know that dz dt is the thing we're trying to find. How fast is the distance between them changing? It might be increasing, it might be decreasing, right? Because Pam's moving closer, but just moving, Rolf's moving further away. Kind of hard to tell. So we need an equation relating the things that are changing. What equation springs to mind? The Pythagorean theorem. So we have that x squared plus y squared equals z squared. Remembering that x, y, and z are all functions of time. If you wanted to, you could write it as x of t quantity squared plus y of t quantity squared equal to z of t quantity squared. If it helped you remember that when you differentiate, you're not just going to get 2x, you're going to get 2 times x of t times dx dt, or 2 times x times dx dt. Derivative of y squared is 2 times y times dy dt. And the derivative of z squared is 2 times z times dz dt. And now we're going to do what we always do. We're going to plug in what we know, solve for what we don't. We should be able to plug in for everything except for dz dt. We should know everything else. We don't actually know everything else. We actually don't know anything else yet. So, yeah. They started 31 miles apart, and Pam was walking 3 miles per hour. Sorry, I keep saying 3 miles per hour, but it's actually 4. I don't know why I keep saying 3. I wrote 3 here, which was not correct. Pam was walking at 4 miles per hour to the east. So if she's walked at 4 miles per hour for how many hours? 4 hours. That means she's covered 16 miles. And if there's a 31-mile distance between them, that means there are 15 miles left. And Rolf was walking at 5 miles per hour for 4 hours. So that means this distance here is going to be 20 miles. And then Z is going to be 25 miles. How do we know that so easily? Because this is a nice triangle. It's a 3, 4, 5 triangle. So there are some Pythagorean triples that do come up regularly in these problems. You should definitely be aware that a 3, 4, 5. Wow, am I drawing that terribly? Kind of. 3, 4, 5 is kind of your nicest right triangle where all the side lengths are integers. But you can take that triangle and multiply it by any number you want, and that'll also be a nice Pythagorean triple. So if you multiply all these sides by 5, 3 times 5 is 15, 4 times 5 is 20, and 5 times 5 is 25. Because Rolf is walking at 5 miles per hour for 4 hours. Right? We started at 8 a.m. We are asking about what's happening at noon. Or you could use Pythagorean theorem, right? You could say 15 squared plus 20 squared equals z squared, and then solve for z. It just feels like it's a little bit more work that way. 15 squared plus 20 squared equals z squared. 15 squared is 225. 20 squared is 400. That's equal to 625. And the square root of 625 is 25. But a lot of the time with these problems, they're going to be set up in a way that where the third side you're missing is easy to find. And you can probably just say, oh, it's a 3, 4, 5 triangle, or it's a 6, 8, 10 triangle, or it's a 5, 12, 13 triangle. Those numbers come up a lot.
So X is 15 or 31?
15. Right, it's the distance that's left from between Pam and where Rolf started out at. All right, so now we get to plug in everything you know. Also, if I wanted to, what could I divide both sides of this equation by? 2. So let's divide by 2 and also plug in what we know. So we know that X is going to be 15. Dx dt is -4. Y is going to be 20. Dy dt is +5. And Z we found to be 25. And dz dt is what we're trying to find. So then over here we have -60 plus 100, that's 40. 40 divided by 25 is equal to dz dt. Or simplifying, dz dt is equal to, let's see, 8 divided by 5. 8 over 5 miles per hour. So at that snapshot in time where Pam is right there and Rolf is right there, the distance between them is increasing at 8/5 miles per hour. All right, it's close enough to 2:30 that we'll stop for that. But related rates, right? It's always the same kind of process. Do you have a question? No, okay. Related rates, the process is always like this. You're identifying what's changing, you're finding an equation relating the variables, you're differentiating both sides, you're plugging in the things you know, you're solving for the thing you don't. That's always those same like 5-ish steps. And then geometry formulas based on whether it's a sphere, a circle, a cone, a triangle, other shapes, a cylinder, all those things. You definitely want to make sure you're familiar with their area and volume type equations. All right, that's all I got. Ready to go. See you all next week. I have office hours as usual, probably pads. And on Tuesday, so who has their exam on Wednesday? Okay, so come with questions. I imagine there'll be some sort of practice exam he'll have posted that we can look at. Also, for those of you on Friday, you should also come with questions because we'll probably do, I guess we'll probably do review both days, but we'll see. We'll see how we do.